Hello, welcome to Chapter 8, homework questions 6 through 12. Write the area of the rectangle at right as a sum and as a product. So we want to write it, probably easiest way to start is as a sum because we have all the individual areas. So let's go ahead and write it as a sum first. Combine your like terms. So we'll start with the x squared. I don't see any other x squared, so we have 2x squared. We have a 4xy. Looks like that's the only one. Then we have a negative 3x and a negative 8x. So that's negative 11x. And then we have a minus 6y here, or negative 6y. And then a plus 12. So the only ones we were able to combine were the negative 3x and the negative 8x. That is the sum. Now let's write it as a product. So we have to figure out what the lengths are. So we're going to do the product next. So what do we have here? It looks like to get 2x squared, we're going to need a 2x and an x. And since the 3x is on top, the x needs to go down here. So if this is 2x and this is x, then we know that if this side is x, then this one has to be negative 3. If we know this is 2x, then down here needs to be negative 4x. And if this side is negative 3 from the other side, I'm just carrying it over. This side would have to be 4. And this side is still 2x. So to figure out what the multiplies to give you 4xy, that would have to be a 2y. 2x times 2y would be 4xy. And this one is a negative 3, so negative 3 times 2y would give you negative 6y. So it looks like we have all the information that we need. I did notice I made a mistake down here on the negative 4x. This should just be a 4 there because you already have the x from the 2x. So the product, we'll do 2x minus 3 times the other side, which is x plus 2y plus 4. So there's the sum equal to the product. Question 8-7, multiply the expressions below using a generic rectangle, then verify Casey's pattern that the product of one diagonal equals the product of the other diagonal. So in part A, and we are verifying from the class notes that the diagonals are equal to each other in terms of their product. So we need to use the generic rectangle as asked. Looks like we will get 12x squared minus 3x plus 20x minus 5. And then if we simplify that, that'll be 12x squared plus 17x minus 5. And we want to verify that the diagonals give you the same answer. So is it true that 12x squared times negative 5 is equal to negative 3x times 20x? Well, let's see what we get. Looks like we get negative 60x squared. And then on this side we get negative 60x squared. So once again, we are verifying that Casey's pattern is correct. Let's go to question B. B, we have a binomial squared. So we really need to expand this out so we can see both of them. And our generic rectangle, the lengths are going to be the same, so it's actually a square on this one. Let's multiply them together. We get 4x squared minus 14x minus 14x times 49. So if we combine our like terms, we'll have 4x squared minus 28x plus 49. And once again, verifying that the diagonals, 4x squared times 49 is equivalent to negative 14x times negative 14x. So we get 4 times 49 is 196, then you have your x squared, and then negative 14 times negative 14 is a positive 196, and x times x is x squared. So once again, we are showing that the diagonals their products are equivalent. Question 8. Review problem 7-108. Write the equation for the following sequence in first term form. So if you go back to question 108 from chapter 7, you'll notice the question talking about another student doing what's called first term form. So that's using the first term. So this would be n equals 1, n equals 2, and n equals 3. So we'll be using the first term instead of the initial term, which we would call it term n equals 0. So let's go ahead and take a look at this. I'm going to set up a table here to kind of help see what the pattern is. So we have term 1 at 500, term 2 at 2,000, and term 3 at 3,500. So we haven't decided whether it's arithmetic or geometric just yet, but if you look at the sequence, 500 to 2,000 would be adding 1,500, and then 2,000 to 3,500 is also adding 1,500. So it does look like it's arithmetic. If I didn't use the first term form, I would have to go back and find what my initial value of term n, or n equals 0, would be. Using the first term form, we're going to only use the first term and not go back to n equals 0. So t of n is equal to, I still have my rate of change, which is 1,500. But now, the difference is here is that I want to be, instead of going back to term 0, I want to do plus 500. I want to start at term 1. But to do that, to start at 500, I need this to be 1,500 times 0, so that when I add 500, I get there. Well, to do that, then if I'm talking about term 1, I need to subtract 1. And that's how we can write what's called first term form, where I'm using the first term, but I still have the 1,500 as my rate of change. And so just to kind of show you that this works, if I plug in 1, I'm going to get 1,500 times 1 minus 1, which is 0, plus 500. So that would be 1,500 times 0 plus 500, and you can see that that was going to cancel out. 1,500 times 0, 0, so that would be 500. And so my first term is 500. I could plug in 2, and then it would be 2 minus 1. So it would be 1,500 plus 500, which is 2,000. So that's what first term form is, and that's that for arithmetic sequence. Let's go ahead and take a look at B. B, once again, I'm going to set up my table here just to help visualize this. So term 1 is 30. Term 2 is 150. Term 3 is 750. And term 4 is 3,750. So it definitely seems like it's going up a lot quicker than linear. So if I work backwards, 150 divided by 30 would be 5. So we're multiplying by 5. If I take 150 and multiply it by 5, I get 750. And if I take 750 and multiply it by 5, I get 3,750. So this one is a geometric sequence. Once again, we want to know what our, not term 0, we're going to use our first term, so t of n. The initial that we're looking at, remember, we want to use our first term, not at term 0, so we want to use 30. And then we're multiplying it by 5, but I can't just raise it to the n power, because that would be 5 times 30. So that's where we're going to do the n minus 1, and now when I plug in 1, I get 5 to the 0. And just remember that 5 raised to the 0 power is 1. So 30 times 1 is 30, and that's your first term form. Question 9. Remember that a diamond problem is a pattern for which the product of two numbers is placed on top, while the sum of the same two numbers is placed on bottom. This pattern is demonstrated in the diamond below. Copy and complete the diamond problems below. So we have negative 80 and 2. So we're looking for, on part A, what two numbers multiply to give you negative 80, but add to give you 2. So you could look at your factors of 80. We're going to have a few of them here, but you can see the first couple, they're really far away from each other. 1 and 80, 2 and 40, so they're not going to add to give you 2. We need something a little bit closer. So then we have 4 and 20. Still not going to work. We have 5 and 16. Looks like we still need some things a little closer together. And then it looks like we'll do 8 and 10. And so we do need a negative 80, which means these numbers will need to be, one of them needs to be negative. And so it looks like the negative 8 and the 10 are going to give us the best option to add to give us 2. So is it true that negative 8 plus 10 is equal to 2? And that is correct. So one of our numbers is negative 8, and the other one is 10. So it multiplies to give you negative 80, but adds to give you 2. What about B? B, we have 12, so x times y gives us 12. And then x plus y is going to give us negative 7. So not near as many factors of 12. 1 times 12, 2 times 6, and 3 times 4. To get a positive 12, we need to multiply a positive times a positive or a negative times a negative. Well, since we're adding, it looks like we're going to need both of these numbers to be negative. So it looks like negative 3 and negative 4 is our match. Negative 3 plus negative 4, it multiplies to give you 12, but adds to give you negative 7. So negative 3, negative 4. Part C. C, we're looking for a product that multiplies to give you 0. So one of the numbers needs to be 0, and then adds to give you 7. So it looks like 0 times 7 would add to give you 7 and multiply to give you 0. Part D. Now it's the other way. What things multiply to give you negative 81 but add to give you 0? Well, to add to get 0, they have to be opposite of each other. So what numbers are going to multiply to give you 81 that are going to be opposite? Well, one of them would be a 9, and the other one would be a negative 9. So they have to be the same, but opposite each other. So 9 times negative 9 is negative 81, and then 9 plus negative 9 is 0. Let's look at E. Now we got some variables thrown in, but let's still stick with the numbers as well. So something, I guess I can't use X and Y now, but we'll go A and B. So A times B is equal to 6x squared, but then when we add those, we want to get 5x. And so you can kind of see your generic rectangle hopefully looking something like this. And to get 6, it's either 1 and 6 or 2 and 3. Well, that has to add to give you 5, so that would be 2 and 3. So 2 times 3 is 6, 2 plus 3 is 5, but x times x is x squared, and then x plus x is your x, or the 2x plus the 3x is the 5x. And f is similar, so you got negative 7x squared and negative 6x. So what multiplies to give you negative 7 but adds to give you negative 6? So that would be negative 7 and 1. And then you need the x times x to get the x squared, and then negative 7x plus 1x is negative 6x. Question 10. In a previous course, you used the distributive property and common factors to change expressions written as sums into expressions written as products. For example, since 6 is the greatest common factor of both terms, 12x plus 18, may be rewritten as 12x plus 18 equals 6 times 2x plus 3. And if you think about the distributive property, that's your 12x, and there's your 18. Here, x is a common factor for every term. So x squared plus xy plus x may be rewritten as x squared plus xy plus x equals, that's x times x times y, and x times 1. Well, I read that wrong, but that's what's multiplied. So x times the quantity x plus y plus 1. Use the greatest common factor to write each sum as a product. So on part A, what is the greatest common factor of 4x and 8? What goes into both of them? And that would be 4. So 4, using your distributive property, is what was distributed to x plus 2. And if you're asking, how do I work backwards? Well, remember, when you're using the distributive property, you are multiplying to do this. So when you're working backwards, you are going to be dividing by that. All right, so let's go ahead and look at B. 10x plus 25y plus 5. I'm going to write this out. Plus 5 is equal to, well, what's in common between 10x, 25y, and 5? Well, 5 would be the greatest common factor. So now you're going to work backwards. 10x divided by 5 is 2x. Okay, so I'm taking this 10x and dividing it by the greatest factor, and that's 2x. 25y divided by 5 is 5y. And then the last one is 5 divided by 5 is 1. So you're working backwards, so you're using division. C, 2x squared minus 8x. So 2 is what's in common between the 2 and the 8. But what else is in common? There's an x. So you also need to take that x out as well. So 2x times what? Well, what's 2x squared divided by 2x? The 2's cancel. Subtract your exponents and you just get 1x. Same thing, negative 8x divided by 2x. So that would be minus 4. Now you don't have to show that work, but I'm just showing you where these numbers are coming from. And D, 9x squared y plus 12x plus 3xy. So I'm going to write it out, 9x squared y plus 12x plus 3xy. So start with the numbers. What goes into 9, 12, and 3? That would be a 3. What about x squared, x, and x? Well, the only thing that's in common is just one of the x's. And then the y's, there's no y on the middle term, so there's nothing in common there. So the greatest common factor is 3x. Work backwards. 9 divided by 3 is 3. X squared divided by x is x. And then y divided by, well, there's nothing there, would be y. To check your answer, is it true that 3x times 3xy is 9x squared y? And that's how you know that you have it correct. Plus 12 divided by 3 is 4. And x divided by x cancels, so that's fine. And then your last one, you have 3x, y divided by 3x, and the 3x's cancel out, so you're just left with the y value. And once again, you can check to make sure that you do have that correct by distributing it back through. 811. On graph paper, graph y equals x squared minus 2x minus 8. Name the y-intercept. What is the connection between the y-intercept and the rule? Name the x-intercepts, and then find the lowest point on the graph called the vertex. All right, so we're going to start by creating a t-chart here. We want to plug values in for x and then solve for y. So let's get some negative numbers in here. 0 and some positives, and we're just going to either plug this into our calculator or we're going to do it by hand. So if you plug in a negative, just make sure when you square it, it's negative 3. It's the quantity negative 3 squared. And I'll do a couple of these and then I'll fill out the rest of the table. But this would be 9 plus 6 minus 8. So 15 minus 8 is 7. And then we plug in negative 2. And on this one, we're going to get y equals 4 plus 4 minus 8. So that would be 8 minus 8 would be 0. I'll do one more and then kind of fill in the rest. So negative 1 squared minus 2 times negative 1 minus 8 would be 1 plus 2 minus 8. 1 plus 2 is 3. 3 minus 8 is negative 5. So keep plugging in those numbers to finish the chart. So I did 3 more numbers. I got 0, 1, 2, and then I noticed that we have a repeat, which is what happens with a quadratic because we know it's going to be a U-shaped graph. And so I can finish plugging in a couple more numbers here by just working backwards with my symmetry. And you didn't necessarily have to show all that work if you were using a calculator, but that's how you can find each of those values. Now, name the y-intercepts. Well, let's go ahead and graph these points first. So negative 3, 7. Negative 2, 0. Negative 1, negative 5. 0, negative 8. What we got? 1, negative 9. And then we work our way back with its symmetry. So let's go ahead and graph. All right, and then now we can answer part A. Part A wants to know what the y-intercepts are. There's only one of them, only across the y-axis one time, and that would be at 0, -8. You can see that from the table or the graph. What is the connection between the y-intercept and the rule? Well, if you notice, when you plug in 0, all this stuff on the front end cancels. That should be a 2. Because 0 is being multiplied and added together, and so you're just left with that last term of the quadratic. So if you recognize that. Name the x-intercepts. It looks like they are at -2, 0, and 4, 0. And then on part C, it wants us to find the lowest point. The lowest point would be at -1, or +1, sorry. +1, -9. And that is called the vertex. Question 12. Calculate the value of each expression below. On part A, 5 minus the square root of 36. So that'd be 5 minus 6, which is -1. B, we have 1 plus the square root of 39. Since the square root of 39 is not a perfect square, we're going to have to approximate this one. So the square root of 39 in your calculator is approximately 6.24. So this will be approximately 7.24. And part C, -2 minus the square root of 5. -2 minus, once again, you'll have to plug in the square root of 5 into your calculator to get an accurate answer. We could approximate it, but 2.24 will approximate that too. And so -2 minus 2.24 would be -4.24. So this approximately, that's what the squiggly lines are, -4.24. And the other thing that you could do, you actually could plug this whole thing into your calculator all at once and get the answer as well, instead of breaking it up into parts.